Don't mind me. Just getting in my morning exercise on the rainbow climbing wall. I've been thinking about a few other things recently, including endlessness. And I've been thinking about it because you talk to people, and I think there's a misconception that infinity is a comprehensible amount. There's this hotel room, as a hotel, and it is a hypothetical hotel, and it has an infinite number of rooms. Okay, and they're all booked by an infinite number of guests. Okay, and you show up, and you're like, oh no, I have to stay at the infinite hotel room, but they're booked out. But the clerk is like, oh no, don't worry. And he goes on his loudspeaker in his infinite hotel room, and he says, hey everyone, move to the room to your right. And then everyone shuffles. And then you can stay in room number 1. Now, management of an infinite hotel room is, obscure. But the point is that these things, that infinity isn't really a number as much as it is a concept of scale. But that's maybe even poor assessment because it goes beyond scale. And that's not the only thing that goes beyond scale and our ability to measure. Something that isn't endless, obviously, is measurement. Just the idea of measurement requires something to be finite in order to be measured. And so, what is it to measure something that is infinite? And thus we get to, I guess, the thing I've been thinking about. When does something become forever? At what point are you like, okay, it's been long enough? Cool thing to find in the woods. Well, another thing about infinity is that there's more than just one type of infinity. Take Cantor's diagonal, for instance. We're going to have a series, S1, S2, S3, on and on and on. Infinite S's, okay? Now, each S corresponds to a system of numbers. In this instance, it's going to be a system of binary. Now, each system of binary is its own unique instance. What Cantor found out was that each of these corresponds to a number. But if you take the first digit of this first one, the second digit of the second one, so on and so forth, you get, and then you get those digits, and then you inverse them. So this 0 becomes a 1, this 1 becomes a 0, this 0 becomes a 1. You take those, you inverse them. You then get a new series, a new notation, a new number that corresponds to not something that's already on our infinite list. Infinity, but an additional one. And this comes up to countable and uncountable infinity. Countable infinity is things like 1 to infinity. Uncountable infinity is things like 0 to 1. Because no matter how far you go, there can still be another 0 on your decimal point. And yet, at some point, you still get to 1. Now, I'm not going to talk about super tasks or anything like that, but this does correlate to the exact thing that we are talking about, where you have a shape that takes up some finite room, you can look at it, and yet there's something going on with its edges, its vertices, whatever you want to call them. And so this issue of measurement arises, I don't know, let's say you're doing some research on if border size affects your propensity to go to war. And also it's 1951, and your name is Louis Richardson. And you're sat there and you're like, Spain and Portugal both have different accounts on the size of their border. Why is that? Well, and you go and you think a little bit more, and you think, well, one surveyor took their line right here because there's no way they want to get muddy. And the other surveyor was a bit more brave and maybe went a little bit further out. And that's only one small part of it. The other part is, where do you draw the line? Do we draw the lake as starting right here? Because after this point it gets impassable. If the water is higher because it just rained, it might be up over here. Anyways, it's called, and it led to, the British coastline paradox. How much coastline does Britain have? For a long time, it was pretty hard to measure. And of course, in modern days, we have radiology, radiometric scanners, and big lasers and stuff. And so we can get pretty exact on how large something is. But what if we're not bound by the limits of size? What if we're existing in a plane of mathematics where an object can have infinite roughness? And so we arrive at the end of our odyssey. It's been a nice day spending it with you. And to close off, where's the point? Where does these ideas of infinity and measurement, where do they lead us to? And, well, as always, the point is vague and convoluted. So, as I was talking about, fractals. So what are fractals? You search it up on the internet. You're gonna get these fascinating spiral designs. And a lot of these are based in mathematical principles. About like numbers interacting on a plot with other numbers. Anyways, these ones are pretty complicated, or pretty standard. The triangles and the snowflake ones. And so what you have with a fractal is you have all these, you have a series of self-similarity. That's the big word, is self-similarity. And that's almost true. Almost. But that kind of misses the point of a fractal and what it is. And so what we're going to be talking about is dimension. So let me get a magic card right here to help illustrate. So you have multiple dimensions, right? Everyone knows it. You can have a line, beep, and that's 2 dimensions, or well, that's 1 dimension. Boop, it's a line. It goes one way. And you have a plane, which will be 2 dimensions. You can go 4 ways. That's a lot of ways. Or we can have what we live in, which is a 3-dimensional space. You know, there's width, depth, length, height, all the gobbledygook. And so a fractal is somewhere in between a line and a plane. You have a shape that is a fractional dimension. Okay, what is this guy talking about? Now, fractals often you have like the zooming nature. This is a bad one. It's not going to let me zoom as much as I want to, but ooh, look at that. It's repeating. Whoa. The shape. It's infinite. And that's what I was talking about. This idea of coastline. That's sort of where these come from. Not entirely. But you have what it is, though, and what the origin is mathematical roughness. You have an object, and it doesn't have smooth sides, right? It actually has kind of bumpy sides. And how do you visualize that in the world of mathematics, right, where things are very boop, 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 boop. And you can use fractals to help you visualize, again, this idea of roughness, right? There's always one more notch. There's always one more zero. And obviously, as I've mentioned earlier, in the real world, there is a limit. You can't get smaller than like an atom or a quark or whatever is at the bottom. But in the world of mathematics, you can. You can keep zooming. And so, what do I mean by fractals? Here, I have a three-dimensional one kind of pulled up for us to kind of demonstrate, to help sort of demonstrate this this idea of dimensionality. And so this fractal would have a dimension of 2, which is weird because it looks like a three-dimensional space. But peek this. If I rotate it to the top, suddenly I'm looking at a plane. My three-dimensional shape turned into a plane. That's cool. And obviously the two-dimensional ones are just a section of this. And so this is what I mean about planes and dimensions, is the fractal operates within boundaries between a one-dimensional shape, your line, and a two-dimensional shape, a plane. And this one's obviously a three-dimensional shape, and so it's kind of cheating. But you're able to, this one's really easy to visualize why this thing can take up a certain amount of space, because it's really just this section of lines and shapes ever repeating. And so yes, it is a self-similar ever repeating shape, but also it is based in the amount of dimensions it takes up, which isn't infinity. Anyways, so there it is. I've had a wonderful semester, and I'll see you on the flip.